I have one more potential change to what I've just discovered, what I've showed you about the dual, coming in with the Fibonacci corkscrewing, both going in the same direction, but a left-hand thread, a right-hand thread, is since the pole finder and the Gauss meter show a north all the way to there, see that? That whole end is showing north, then it shows south from there into there. And, the dead spot is what I said it was, but since we've got such a long stretch of north here and a small dead spot in the middle, and if I lengthen the magnet, it just lengthens that dead spot. The whole blue doesn't show and the whole red doesn't show till I get out here on the south. And that dead spot's lengthened. What I'm thinking possibly is instead of the torus feeding out of the magnet here and back to itself, I think it's kind of a one direction of the dielectric coming in only. It just slows down how much is coming in, and I'm going to show you why. And this side is the same, but they come in and meet with the same rotational problems I've shown and I will show in the rest of this video. But I'm thinking instead of it looping back around to itself, it's possible it's just coming in, but slower here than it is out here where the Fibonacci's fast. So the Fibonacci's quick on the end and gets slower, but it's all coming in and it just gets slower here. And this one is reverse, same direction of rotation. It's quicker out here on the end and then slower rotation as or Fibonacci pull in as you get there. Slower pull in to the magnet. Right in between them, it's more gravitational, could be coming from the ether, or it could be the Fibonacci spins just slowed down inside the magnet. But outside the magnet, the way the pole finder and the Gauss meter shows, it's coming in all the way to there. See that? So from there, all the way to there, in between there, it could be gravitational, but I think it's coming in until the light stops, or where the Gauss meter says it's 0 in the middle, then it will jump right to negative as soon as you get away from 0, and this one will jump to right to positive on a Gauss meter. This just doesn't pick up that delicate of movement. It has to be real fast out here. This should pick it up all the way to the line and then stop. And then from the line on, it should pick it up, but it doesn't till out here, you see. Okay, before I get to showing you how I think I know how Hall sensors work, whether academia knows or the industry that makes them and everyone knows what I found out. But what got me on it was, the rotation of a magnet. If you see the arrows here, they're both coming towards us, the red and the south, or the north and the south. And if you put this towards a TV screen, it'll rotate clockwise, south to you, north to the screen. Like I've showed 1,000 times, if you put the north to you and the south of the screen, it rotates counterclockwise. And I went through the wheel and showed everybody that. And since I've changed my explanation of magnetism, that they're each feeding in a corkscrew in the same direction. And my next video is going to show why that does that, or how it does it, why it ends up being corkscrewing in the same direction. But this video is more about how the Hall sensor proved that this is what's working. Because what happens, I had to do extensive experiments with Hall sensors, like on my Gauss meter and on this pole finder, to find out why they do what they do. Because no matter how you orient the magnet to the Hall sensor, if you see that, it stays red. And if I go behind it, no matter how I orient it, it will stay green. You see that? Because you're on the reverse side. But it's the rotation, not just the rotation, but it's the direction of flow. The Fibonacci's coming in on both ends. But there's a change I'm going to make to that. But the point is, the reason I had to use Hall sensors to figure this out, the change I'm going to show you, is because it's always the same. But if you notice, if this picks up only rotational direction, let's say we'll use the south. If you look at this, it's rotating up into the sensor from the back side there. And this way it's rotating, towards the back of the sensor. And this way it's rotating down into the sensor. You see what I mean? Always rotating in the same direction, but it moves, when you apply it in different orientations, it's a different direction of rotation towards the sensor. But even though our magnet's doing that, it always shows a south. No matter how I orient the rotation towards that sensor, it always shows a south. So I want to explain how I've changed a little bit of how the toruses work because of this. What I found out is why the sensor does what it does in the same, any orientation, it'll show that as a south. The north, any orientation, it will show that as a north. The only time it changes is if I get behind it, because it's showing it from rotations on the other side of the sensor. Just like this. Instead of being on this side of the sensor, it's on that side. So I'm reversing which way the rotation is applied to the sensor and which direction the feed's going. The feed's going the same direction, but the rotation switches, if you see what I'm saying. Anyway, this and the Hall sensor with this is what caused me to change a little bit of what I'm saying is happening. And what I changed, there's still two toruses, you know, a blue one on the south side, or a south torus and a north torus. They're both rotating in the same direction, and they're both feeding in towards each other. You know, the center of Fibonacci is going in this way on the south and the other way on the north. The difference I'm going to make is it's not feeding in and looping back around like we show a torus doing, a torus knot. The whole torus is coming in to the magnet on both sides. They do not feed back to themselves. They just feed inwards. That's it. Inwards, but they're rotating as they feed in, and they rotate in the same direction. Like I said, my next video, I'll show you why they both rotate the same direction. There's a reason for that. But anyway, this is what I'm going to show you how Hall sensors work and why it changed my theory on the toruses rotating back into themselves. They don't. They just rotate inward and meet each other and kind of cancel each other out to a slower speed in the middle of the magnet. That's why the dead spot there. But I understand now more how that works because of a Hall sensor. So I'm going to show you how they work with some demonstrations, and we'll move from there to doing that with electric current. So we'll move on to that. Okay, on the Hall sensor here on your left, it's the same thing that's in a pole identifier on your right, same thing that's in Gauss meters. It just determines which is south and which is north. And I finally figured out how they work. I don't know if everyone else knows, or the industry or academia, because it's how the magnet, I've changed the rotation, and the Fibonacci corkscrewing is what causes the Hall sensor to do what it does. And that's why I changed how the torus works. It doesn't feed back to itself. It's all feeding into the magnet from both sides, left hand and right hand, towards each other. So here's the Hall sensor. It's just a metal plate with the current running straight through it from left to right, the big arrow in the middle. When you put a magnet near it, the south will push the current towards the positive or the negative, depending on which side of the plate you're on, and the north will push it to the reverse, and then it reverses on the other side of the plate. And if you run the current the other way through this, it reverses everything again. So there's several different ways you can wire a Hall sensor, like in a pole finder or a Gauss meter, but it will be reversed. I mean, it'll show you that a north is a south and a south is a north. So they have to wire them just right to know which is which. So here's my little push of how a Hall sensor works. There's our metal plate. We've got our red current coming in on the left and our ground in the middle going out on the right. And on the top is our north ground, which will pull a north reading, and on the bottom is our south ground, which will pull a south reading. So depending on which pole of the magnet you put to this side of the plate will give you a south or a north. And it reverses on the other side. So here we are. I push the button. So now the current's going straight through from left to right, right down the middle of the plate. There's no magnet near it, so it's just on. I've got it on, but the lights are not lighting up because there's no magnet pulling the current one way or the other. So now we're going to put a south pole of a magnet towards it, and that's what it does. It bends it. It twists the current over to that south wire, and it grounds through the light, and the blue light or the green light shows up, the south light, because that Fibonacci and rotation, the two directions of movement, cause it to do that. And If you take the magnet away, then your current goes back to the middle again. You got the button held down, but neither of the lights are on. That's because there's no magnetic field bending that current. Now, if I put the north up against it, it bends it upward or to the other side, and the red light illuminates. It grounds through that light. And it'll always do this. And I'm going to show you next with some electric currents how this actually works. It'd be like if we're looking inside of a hall sensor, what it's doing. And so we'll run to a little picture here. It shows these pictures of how it works. So the south will push it to the south pole on the hall sensor, and the north will pull it to the north pole. Like I said, they've got to be wired right and to know which is north and which is south, because you can put the magnet on the back side and it reverses, or you can run the current through it backwards and it reverses. So, you have to have the three things in configuration. Okay, now we'll move on to some electric current demonstration that shows you exactly how this works. Okay, I've got my electrodes here with my 15,000 volt, 30 milliamp NST or neon sign transformer. I'm going to take a cloth and cover the transformer so you can see the electric current better, okay? I don't have long enough wires to set this way off to the side. So that's why the cloth is there. But like I was showing you, or it showed just prior to this, is a hall sensor has those three wires, and there's a current goes straight through, just like this. But anytime the magnet pulls it to one side or the other, it'll light up one light or the other. And I may show that drawings again. That's how this works. That's how the Gauss meter works. They all work off the same principle. So what we know is when you apply the rotation to that electric current, no matter how I apply either pole, that rotation to it, it always stays with the same light on. It's bending that current in the same direction, even though the rotation is changing directions that it's applied to the hall sensor. No matter which pole will always stay the same, no matter how you apply the rotation, south or north. I understand why that does that now. And it's like I said, they're both rotating in the same direction, but they're feeding towards each other. There is no loop back on the torus knot. It's just a bulb coming in and a bulb coming in, corkscrewing towards each other, but in the same direction. Left-hand thread, right-hand thread. So what's happening, and what I'm going to use to show you, I'm going to use this bigger magnet because it really bends the electric current. So when we apply the south, remember, if we're looking at the south here, it's rotating clockwise. So straight down, it'd be rotating this way. Okay? And this way, it'll be rotating over the top away from us, and this way, it'll be rotating over the top towards us. So just remember, it's clockwise this way, that way, okay? Keep that in mind. We're going to use the south first. So as I turn the current on, if you notice, it pulls it into it. But it doesn't matter which way I angle it, it's pulling it into it. Even though it's rotating different according to the direction of rotation, it's pulling it into it. You see that? Always pulling. And that's because the rotation is not just rotating around, but it's also feeding in one direction. There is no loop back. And I'll show you the north side in just a second. Okay, now we're going to put the north to it. If you noticed, on the south, it was always kind of pulling the charge towards us, no matter how I oriented the south. Now watch the north. No matter how I orient the charge to it, or the rotation, it's pushing it away, if you notice that. It's pushing it away. No matter how I orient that rotation, it's pushing it away, okay? And the difference on, plus or minus on a Gauss meter or the red or green on the pole finder, like on this side, it shows a north. But on this side, it'll show a south. See that? South on this side, north on this side. That's because when you apply the rotation this way, on this side, it pushes. No matter how I orient, it pushes. And on this side, the north will pull, see? And now I'll tell you why that does that. It always follows the direction of rotation for the electric current wants to stay going. So it pulls in with the rotation and lets go as it goes past it. So it's always going to pull in, whichever way that's rotating, it's going to pull in that direction. And you've got to get this. It's either, right now it's rotating this way. So it's going to pull it down into the bottom of the magnet. It's going to push it away because it does that. It pushes out as it goes over, so it's pushing it away. This way, it's rotating the other way, so it's pushing away because it's trying to go to the bottom of the magnet, down to with the rotation. Comes in with the rotation, goes out with the rotation. And it has to go almost around the magnet here to do it. If you see, it's coming in on the top and coming out on the bottom. Here, it's coming in on the bottom and coming out before it even gets to this side of the top. That's why a Hall sensor does what it does. The direction of rotation plus the feed coming in on both sides, there is no back feed. It's all coming into it. That's why that rotation does that. No matter how I apply the magnets, rotation, let me use this. No matter how I apply that direction of rotation, if you see that, it's going to catch it over here, or on a north, it'll catch it here and pull it down and pull it towards us. Oh, I'm sorry, I'm wrong. The north pushes it away. It follows the rotation over the top here. It goes in with it here, around, and it follows it around to the bottom there and pushes it out. It just comes in whichever way that feed is coming in. It goes on that side, then out. This way, it goes in on this side, then out. But it's always pushing. When I flip the magnet, the south is doing the opposite. It's coming in this way, so it's pulling it under, pulling it to us. This way, it's going with it, pulling it to us with the feed of the Fibonacci. And this way, it's going over the top, going under, pulling it to us. Basically twisting it. But that's what's happening with the small electric current in here. That is why I was befuddled of how that direction of rotation will keep that magnet, or the direction of rotation is changing on the magnet, but the Hall sensor still knows which pole it is. Okay? It still knows, because it's not the rotation it's changing, but the electric current has to continue to go across, so it'll take the shortest cut. And it goes with the rotation over the top or underneath. It doesn't care, but it continues at corkscrew. The corkscrew is key. The two motions, the rotation and the corkscrewing, is why a Hall sensor does what it does. I may run them pictures and animation again and show you, but that's why it does what it does. That's how I know that the Fibonacci's are both feeding inward only. There is no run back on the toruses. They are feeding in only, or that wouldn't show. And I have one more demonstration I'll show you that proves that. If I have the magnet, I'm going to use the bar for this one. If you notice, maybe I should go on this side. It's always pulling it towards the magnet, towards the center. And the south does the same thing in this orientation. It's pulling it over. And that side, they both push it. That's the direction of rotation. But the south kind of pushes it up, and the north pulls it down. Well, pushes it down. Pushes it down, pushes it up. And this side will pull it down, and that will pull it up. The blue pulls it up, the north pulls it down. That's the same thing, is because not only is it rotating and corkscrewing, but they're both going towards each other. There is no flyback, run back. It's just coming in here and coming in here. That's why the current does what it does with this, and that's why Hall sensors work the way they do. Okay, one more little thing here is, just like depending on which side of the current I'm on, with the rotation and the Fibonacci feed direction, the two motions, it's the same thing as if you switch the current, the direction of current. I'm DC, positive to negative. So the DC is always following the rotation. If it's coming this way, the rotation is that way. It's going to pull it in the bottom and release it on the top. So it's pulling it towards me. And even when I turn it this way, it still pulls it towards me because it's going in on the top and down to the bottom. But when I flip it on this side, it reverses. It'll start pushing it. It'll push the current this way, or no, it'll pull it that way, this way, or pull it. This side, it pulls it that way. This side, it pulls it this way. That's why on this side, it shows a south. This side, it'll show a north on the Hall sensor. Say this side of the Hall sensor, let me do this. This side, it shows a south. See, I got my sensor right where the poles are. South, I get over here and it goes north. If you see that, south or north, because it pulls it the opposite direction. The current wants to keep going straight ahead. On one side, it pulls it over the top. The other side, it pushes it out under the bottom. And the north is reversed. Or if you reverse the current, you can reverse this. This side would be what a north would normally do. It all depends on direction of current and which way you orient the magnet, north or south. Same thing here. All they have to do is know which way the current's going through the end to line the other two wires up to whichever light lights up, depending on which way they've run the current through it. That's all it is.